Let's get started. Let me share my screen. Everybody, could you see my screen?
Yes.
Yeah. Like as you can see today, we will be discussing couple of points about synchronous generator. First one is called open circuit characteristics or magnetization curve, and then we will be looking the equivalent circuit for the synchronous generator. And one concept is called armature reaction, and their phasor diagrams. And by utilizing the concept of equivalent circuit and phasor diagrams, we will be looking the voltage regulation. And then one thing is called the PMSG, permanent magnet synchronous generator. So first of all, that open circuit characteristics. So you see here I have written that open circuit characteristics, sometimes it is briefly called OCC, or the magnetization curve, represents the terminal voltage versus the field current characteristics of a synchronous generator. And then I have written that voltage production depends on field flux and rotary speed. So what does that mean? Uh, just a moment. Let me take you to that whiteboard. So, so in this axis, that field current, IF, and in this axis, that voltage development in a synchronous generator. Now, you see, if you see that voltage equation that we did, let me write it, voltage or that 4.44 and then phi f n, and then there was that kW. So if you remember, probably we use the symbol E, but it does not matter. It is the same thing. So if you see that this is constant, frequency is a constant factor. For a specific generator, this number will be constant. So main thing is that phi, and then your number of turns. But just a moment. You see, so this is the speed, and then for example, just I'm showing one phase of the generator on the stator. So here is that flux which is generating from the coil, and then of course there is actual magnetic field, north pole, south pole, which has also the flux, and then this is the speed. Now you can say that that voltage is proportional to the two factor. One thing is that omega, other thing is that phi, the flux. So now you can assume that speed is almost constant. Speed is coming from the prime mover unless there is any major disturbance in the system. That speed you can assume the constant. Now the main thing is that flux. So that's why here that flux or the field current, so flux or the field current versus the voltage. So how the voltage build up? So this is the zero position. Now according to this equation, if you see if the phi is zero, this means the voltage build up will be zero. And then as you go upward, gradually if you increase the field current or the flux, so the voltage will increase. So it will go in that way. So you see, this is the like linear approximation, linear variation. But in real practice, what happened? That you are increasing the field current or the flux is increasing. I mean, the gradually. But at some point, what happens? The voltage does not increase. It looks like it was going. Then after some point, it becomes like that. So this is the ideal curve, but this is the saturated curve. So at some point on, what happens, even though you increase the field current or the flux, but voltage does not increase. because the flux or the field got saturated. That is the property of that magnetic material. Field got saturated. So therefore, this realistic curve is called your open circuit characteristics curve, OCSA. So this means a generator just produced the voltage you may or may not use. So it is open circuit. Unless you connect to the load, it is the open circuit. That's why this curve, like voltage versus the flux or the field current, is called OCC curve. So this is the kind of the ideal one. This is ideal curve, but this one is the realistic curve, which is the OCC curve. So therefore, simply OCC curve is the voltage versus the flux curve. Just to keep in mind. Now, one thing is that you see here I have started from zero. So according to the equation, if flux is zero, voltage is zero. That is right. But sometimes it happens that even though there is no flux, for example, you are doing the lab, you are doing on lab experiment, and you start a generator and you are measuring the terminal voltage. At the very first attempt, you might get some voltage. For example, you might get, for example, 2 volt, you might get. So therefore, curve might not start from here, curve might start from here, 2 volt, or it could be 1.5 volt. This is due to the residual magnetism. This is due to, it is called the residual magnetism. This means that, for example, today someone worked, today someone used the generator and the field was excited. And then you stopped the experiment. The next day or 2 days later, the someone came, other group came, and they made the same experiment. In that case, at the beginning, they might get some voltage, not big voltage, small voltage, typically 1 volt, 2 volt, or 2.5 volt in that range. That is due to residual magnetism, remaining magnetism. Some flux was remaining. So therefore, according to this equation, although phi is zero means the voltage zero, but at the beginning, you might get some voltage. So you would not be surprised with that. You will keep in mind that that is due to residual magnetism. Everybody, could you follow me what I'm saying? So what I'm saying that the curve might not start from, curve might start from some voltage value. And that is due to residual magnetism. I mean, even though you are not exciting the field, already there are some flux, the little flux, that may cause some voltage at the starting. And then of course you need to excite the field or apply the field current, then gradually voltage will build up. So I'm talking about this initial one. So this amount is called that residual voltage due to residual magnetism or remaining magnetism. So therefore now go back. Sorry. Yes, I was here. So therefore you see, that is the thing I have written here. Open circuit characteristic, OCC, or magnetization curve, means the terminal voltage versus the field current of a synchronous generator. And then voltage production depend on field flux and rotary speed. Those two are the main thing. I mean, of course, there are number of coils, frequency, winding factor, other things are related, but these two are the main factor. And then this curve means we assume that rotary speed is constant because that is coming from the prime mover. We are assuming there is no issue, no disturbance on the input side. So therefore, voltage development or production fully depends on the field flux, or in other words, the field current. Okay, so now moving forward, we'd like to see the equivalent circuit of synchronous generator. So how we can represent? Like before we looked for transformer, we looked for induction motor. Now we will be looking for synchronous generator. So therefore, as you can see, so here I have shown on picture from you. So we are following that book. If you see that book, uh, you know that synchronous generator has two parts, two component. One is the stator and other one is the rotor. So on the rotor, the shaft is attached, but the magnetic field, physical magnetic poles are placed on the rotor circuit. So that's why you see this is the rotor circuit representation. So rotor circuit representation means there are physical magnetic poles and there are windings or the coils to excite the field. So it is mainly the inductance, but it has some resistance. That's why, and then you will be applying the DC voltage. So therefore, field current is going to that magnetic field. That is the meaning. And then you can vary the resistance to control the field current. So therefore, left side, this portion is the representation or equivalent circuit of rotor for the synchronous generator. Just a coil and in series variable resistor, which is called the rheostat. Now, on the right side, so there are three figures. Those three figures are for three phase. This is for A phase, for B phase, and C phase. Now, this portion is for the stator. And you know that for synchronous generator, coils are placed on stator at which the voltage will build up. So that's why for phase A, it is representing the voltage built up, initial voltage built up, which is called internal voltage. And then coils are represented by resistance and a reactance. And you see the symbol I have used XS. So RA stands for armature resistance. Current flowing is armature resistance. And EA is internal voltage across the armature coil. And this is called the terminal voltage of the armature. But XS is called the synchronous reactance. So in next slide, I am coming in detail. XS is called the synchronous reactance. Because this is synchronous generator, accordingly, you keep in mind XS is called synchronous reactance. So this means that the same thing goes for B phase and C phase. So simply speaking, for synchronous generator, stator coils have its resistance and a reactance. And this is the terminal voltage. And if loads are connected, then current will flow, which is IA. And EA is the internal generated voltage. Yeah, this means that the equation that I showed, that 4.445 in kW, this is actually that one. And V is the terminal voltage. After deducting the voltage drop due to resistance and reactance. Just keep in mind. So therefore, in our equation, this is the voltage that you will get by using that equation. But this is the terminal voltage. And actually, this is the usable voltage. This is the useful voltage. This voltage is available at the terminal that people can use if the load is connected. Now, how that I'm getting access? So let's go to that next slide. Then it will clarify you. You see, now I am analyzing much more detail. Again, this is that internal voltage. And that V this symbol, this represents the terminal voltage. And here I have introduced another voltage. You see the difference? Here it was just two components, resistance and excess reactance. But now I am decomposing this excess into two components. You see, there are two coils. There is one coil here, other coil is here. Array is the same. So XA, so you see I have written this one, that is called leakage or self-reactance, which is XA. And then other reactance, XAR, which is called armature reactance. And then the total thing, XA plus XAR, that is called the XS, synchronous reactance. So this means if you sum up these two, XA plus XR, That is the synchronous reactance, which was available in this picture. Now, why that this one is coming, XAR? So let me explain. So everybody see here, uh, just look this one, because the field circuit and this one side by side, so it is much easier to explain. So everybody look this one. For example, the load is connected. So if the load is connected, then current will start flowing. It is not open circuited. And once the current will flow, through this coil, then this will produce another magnetic field, another flux. So you know the property. Once current flows through any coil, it produces flux. That is common. So therefore, and then this is the main field flux. Of course, this is the magnet and it has already been excited. So it is producing flux. So this is its flux, and then this is another flux. Now it has two component. One component is the self or the leakage. It is just moving here. But the other component is interacts, it links with this one. This means some portion will be interacting here. And then what will happen? Actually, it will oppose the main field flux. The portion that will link or interact with the magnetic field, main field, it will deduct some portion. So some of the magnetic field will be reduced because of that interaction. And then that will cause some voltage drop. So to represent that on that situation, XAR present. So, and then that is called actually the armature reaction. So here everybody see, I wrote down on definition, armature reaction. It is the interaction between the main field flux and the flux produced by the stator or armature current. So once again you look, armature reaction means interaction between the main field flux and the flux produced by the stator or armature current. So this means that once the current is flowing, you are getting on flux. So this is called the armature flux. And this is called the rotor flux is called the main field flux. Because at the beginning, when no current is flowing, this flux is present. This flux is always present because this is needed to build up this voltage. Once this voltage build up and you are connecting the load and current is starting flowing, then that is producing another flux here, and that flux is opposing or interacting with the main field flux, and that ultimately reducing some of the main field flux. That phenomenon is called the armature reaction. So because it is reducing some of the main field flux, and the effect is that some of the voltage is getting dropped here and here, this means certainly there is on action, there is on reactance, which is called that XAR, armature reactance. Therefore, leakage or self reactance means the main inductance of the coil, of the stator coil. RA is its resistance, that is fine. But XAR is coming because of that armature reaction, because of this phenomenon. Just keep in mind, because of that armature reaction phenomenon. So that's why we have to take into account. So this means that what happens if you start from the terminal, this is the terminal voltage, and then gradually you have to subtract that, gradually you have to add the drop, IARA, and then again IA multiplied by JXA, then you will be getting on voltage here. This is called the air gap voltage, E phi, this symbol. V phi is terminal voltage, E phi is the air gap voltage. And then if you add the other drop, that IA multiplied by JXR, then ultimately you will be getting internal generated voltage. So that's why you see that from here, this array is this array, and XA and XR, as I have written at the bottom, synchronous reactance, that is added up. So that's why it is JXS. So then simply RA plus JXS, you can represent by symbol GS. GS is that synchronous impedance. Therefore, I mean, from today you will be remembering this term. Soon I will be showing you one numerical problem, and then that will help you to understand. So therefore, if you see this diagram or this diagram, you remember the terminology. EA is that internal generated voltage. Internal generated voltage. V phi is that terminal voltage, or which is the rated voltage. This one, if high, you will be calling the air gap voltage, and R is the armature resistance, XS is the synchronous reactance, and XA is the self or leakage reactance, XAR is the armature reactance. And so therefore, I mean, either of those picture is the equivalent circuit of stator or the armature circuit. Everybody, could you follow me so far? Is this fine? Okay.
I believe so, yeah.
Yeah. Okay. Great. And then now again moving. So today we'll be looking, I mean, soon I'll be looking on numerical problem. That time again, those synchronous reactance, armature reactance, though everything will be popped up, and you will be understanding clearly. Uh, in the numerical problem, we will be finding the voltage regulation. So voltage regulation, the definition is no load voltage minus full load voltage taken as a percentage of full load voltage. So no load voltage means when there is no load connected. So therefore, once again, if I go in this picture, for example, this is the equivalent circuit, but no load is connected. Means no current is flowing. IA is 0. If IA is 0, this means that here you will get this voltage. So therefore, this one will be your no load voltage. So therefore, based on the problem, you have to find out the EI. That will be no load voltage. And full load voltage means this terminal voltage. That is called the full load voltage, assuming that the current is flowing, the load is connected. So that's why everybody, you will be remembering this equation, no load voltage minus full load voltage. And voltage regulation is very important in power network. Uh, because it indicates, voltage regulation indicates how much better or how much effective your system is. If you see that there is huge difference here between no load voltage and full load voltage, this means the voltage regulation will be poor. So it is the expectation that voltage regulation value will be like 10% or 15%, not more than that. That is the expectation. I mean, today we will be solving on problem. You will be noticing that voltage regulation value is very high. I think more than 50%, means that is called the poor regulation. So it is the expectation that this difference is low. So only then you will get the high voltage, sorry, the low voltage regulation value. So let's have a look on numerical problem, and then you will get. On example 7.3, everybody read the problem. A three-phase 13.2 kV, 60 Hz, 50 MVA, Y-connected cylindrical rotor synchronous generator has an armature reactance of 2.19 ohm per phase. So everybody say, so at the very first line, that 13.2 kV, that is actually, I mean, the 13 kV, 60 Hertz, 50 MVA, these all represent the rated value of the generator. So this means this is the rated or the maximum capacity. So similarly, 13.2 kV is the maximum voltage. That is that is the rating. And this voltage is available at the terminal. So everybody keep in mind this voltage is available at the terminal. This is not the internal generated voltage. This means there is internal generated voltage, and then you have to subtract the armature reactance drop, resistive drop. Only then you will be getting this one. Now, the armature reactance has given 2.19. the leakage reactance is 0.137 times the armature reactance. The armature resistance is small enough to be negligible. So the problem is saying that RA value, armature resistance value is negligible. So assume this is 0. That is the meaning. But again, there can be any value in other problem. So that is fine. Also ignore the saturation. This means just consider the ideal case. Now it says, assume that the generator delivers full load current at the rated voltage and zero point 0.8 lagging power factor. Then determine the following. What is the synchronous reactance in ohms per phase? The rated load current, the air gap voltage, the internal generated voltage, the power angle, and the voltage regulation. So there are a couple of questions. So therefore, now go one by one. Here I have that solutions. So everybody see, first of all, synchronous reactance. So we said that synchronous reactance XS is XAR plus XA. XAR means armature reactance and XA is the leakage or the self reactance. So you see the problem. A synchronous generator has an armature reactance, ohms per phase. So this means 2.19 is the value of XAR. So that's why I have written XAR is 2.19. And what will be X? That will be 0.137 times of that. So then by multiplying, I am getting 0.3. And see the statement? It says the leakage reactance is 0.137 times the armature reactance. So this means of that value. So this multiplied by this one, leakage reactance or self reactance, which is that XA that I did. So then now you sum up, then you will get synchronous reactance. So I got synchronous reactance 2.49. Now the next question is the rated load current. Rated. So therefore, you see, as I said at the beginning, that the very first line, those are the ratings of the generator. Those are the rated values. This voltage, this MVA. And then it says generator delivers full load current at the rated voltage and the 0.8 lagging power factor. So therefore, to get the rated current, we have to utilize these two numbers. 50 MVA, definitely this is the apparent power because this is not in expressed megawatt. This is not the real power. This is the apparent power. And 13.2, the other thing is that everybody keep in mind, when it is three-phase system, by default, this value is the line-to-line voltage. This is not the phase voltage. If it is phase voltage, it will be clearly mentioned like 13.2 kV per phase. So when it does not say anything, this means by default, it is standard practice. I mean in power network, this voltage is line to line voltage. Just keep in mind. But then the other quantity, look here, armature reactance, that is clearly says ohm per phase. Similarly, the leakage that will be ohm per phase. But these things, these are the rated and line to line. Just keep in mind. So therefore, the rated load current you will be calculating by using these two numbers. So therefore, see that one is root 3 VLIL because three-phase system. So I'm using the apparent power equation, which is 50 MVA. And then from there you get IL value. Therefore 50, I converted into volt ampere. Then VL, you see, that 13.2 kV multiplied by 10 to the power 3. I converted into volt ampere. So I got 2186.93 approximately ampere. Oh, and then power factor value was given, you see, 0.8 lagging. So that's why I just cos theta. Theta I calculated 36.87 degree. I mean, later I will be utilizing this theta. So far, everybody, do you understand these things?
Yeah. So far we're good.
Yeah, right, great. So now you see the next question was, first see the question. Next question was the air gap voltage. So therefore, once again, which on that on air gap voltage? Look this picture, this one, this voltage, this voltage. So therefore, once again, this is terminal voltage. Terminal voltage is in that problem that 13.2 kV, which is the rated value. But air gap voltage means you have to find the voltage here. And this one here means internal generated voltage. So this is the like highest voltage. Then it will have some lower value, and then it will have further lower value because you have considered this drop. So therefore, everybody say based on this diagram, you have to find out air gap voltage means the voltage here. So this means you know this voltage, terminal voltage, which is the given in the problem 13.2. Then what you will be doing? You have to sum up this drop, IARA drop. Also, you have to sum up this drop, IA into JXI. And you know what is the XA value and what is the RA value. So that's how everybody see. Yes, what I have written that air gap voltage is VT, terminal voltage, plus IA multiplied by RA plus JXI. And then, of course, this is the per phase equation. So you keep in mind this equation for per phase. This is for phase A. So this equation per phase. But then that VT voltage was given line to line, as I said. That's why see my next line, 13.2 divided by root 3. Because you see the system was Y connected. Look the very first line at the end, 50 MVA Y connected. Because Y connected, this is line to line voltage. To use in the equation, I have to convert this on into phase voltage. That's why I have to divide it by root 3. So I divided by root 3. And then this IA, because this is Y connected system, so IA phase current and line current is the same. So that's why you say for IA, I am using the same number. Everybody see? But then what I am doing here, now because I am going the phasor, you see, this is the vector or the phasor. Now I have to consider the angle with the current magnitude. I mean, the magnitude answer was fine for the part B, but now I have to consider the angle. So what is the angle? That power factor angle, that theta 36.87. And because it says, you see, the lagging power factor, 0.8 lagging power factor, so the angle will be minus. So that's why see this one, IA this one, angle this one. And RA plus JXA, you see, RA value is 0. The problem says, you see, the armature resistance is small enough to be negligible. This means that is 0. So therefore, only I have to consider the JXA. So this means what is my XA value? Look, my XA value is 0.3. So therefore, J 0.3. I have written this one. And then just go ahead, just go with the phasor. From here, I got 7.62. Next time I converted into volt because this was in ampere. So definitely this is in volt. This portion will be in volt. So angle 53, and from there I converted into rectangular. Finally, I summed up, and again I expressed in the polar form. So 8030.82 angle 3.75 degree volt. So therefore, this amount, this magnitude is the your air gap voltage. That was the question. So everybody, could you follow me?
Yep. So far so good.
Yeah. So therefore, just you need to look this diagram, then you will be fine. If you can just remember this diagram, if it is available in front of your eye, then you will get it. Internal voltage, air gap voltage, this is terminal voltage. So therefore, as I said, this is the highest voltage, this is the lowest voltage, and this is somewhat between. So accordingly, like you have to calculate. If you know the current and if you know these values, then you can sum up and ultimately you can reach here. That is the thing. So therefore we are fine up to now. We got that one. So the next question is, everybody say, question number D, internal generated voltage. So internal generated voltage means ultimately this one. So then so far we have been able to calculate this one. Now I have to add this voltage drop to get this voltage. This means current is the same, you see, I. So just multiply with this one. This is the armature reactance, XR. Then you will be getting this one. Therefore, see my calculation. EI, internal voltage, Fi, which means the air gap voltage plus JIXR. So therefore, F's value, from the last calculation, I got this amount, and then J. Again, I am substituting I value, that magnitude together with the angle, and then XAR value was 2.19. That already we calculated. And then again, you just calculate. And finally, I got 11,726.24, angle 21.8 degree. So this is the, you see, you got the highest number, 11,000, and this was the 8,000, and I think terminal voltage magnitude, I got 7,620. So that makes sense. So therefore we are done. So this is the result for the internal generated voltage. Now there are two more questions, power angle and finally the voltage regulation. So power angle, so you keep in mind the angle with the EA, this means internal generated voltage, is called the power angle. Sometimes it is called the torque angle. So the power angle or torque angle is the angle which is available with the internal voltage. Therefore, straightforward, that is the answer. Whatever the angle is, that is the power angle. And also soon I will be showing you one vector diagram for synchronous generator. That time again, it will be clear to you why we are considering this one as power angle. At this point, everybody just keep in mind the angle with the EA is called the power angle. Now, the last question, voltage regulation. So you know the definition, no load voltage minus full load voltage divided by full load voltage and then make percentage. So full load voltage is that one, terminal voltage. This is the full load voltage. And the no load voltage, which is the internal generated voltage. So that's why everybody say this is that 11,726.24. Here, to calculate voltage regulation, you don't need to take the angle into account. You just need the magnitude. So that's why this portion is the no load voltage. And then 7,620, that is the terminal voltage. Here you see that I got 13.2 over root 3, that's 7620. From there I wrote, and then divide by full load voltage. You see that I got 53.8%. So this means this is very bad for the generator. The reason is that low lagging power factor is going to the load. The customers are using huge low lagging power factor that is causing huge drop. That's why you see there is huge difference in voltage, kind of the 4,100 difference. That is too much. That's why you are getting the very poor value. So it is the expectation that when there is no load, the difference is very low so that you get the small number here. As I told you, expectation is like 10% or 15%. Then the system is pretty good. System will have less loss. There will be less reactive power loss. Power factor will be much more improved. In this case, mostly lagging power factor that caused the huge voltage drop. So that's why the regulation is high. So everybody, could you follow the process, how to calculate these things? So therefore, key to is that you just remember this one. Everybody remember this diagram and just remember the meaning of the symbols, then you will be fine. Once again, this is terminal voltage, air gap voltage, internal generated voltage. So when you are calculating voltage regulation, you need to know this one, EI, which will be the no load voltage. Because if there is, you see, when there is no load connected, IA0 means there is no drop. So only this voltage is available, which is no load voltage. And once it is loaded, system has some loads, then this is your terminal voltage. So this voltage is given in the problem. So you need to know this one. Then you can calculate, and then rest of the things depends on the problem. In this case, air gap voltage, and then synchronous reactance value, rated current, etc. So I think everybody got that on. You will be looking once again. Now, a new topic you see here, effect of excitation slash field current on power factor of synchronous generator. You see, I mean, as I said, that two factors are dominating, two factors are important in voltage development in synchronous generator. One is the speed, and other thing is the excitation or the field current, because you have to excite the magnetic field. So depending on the excitation, if you apply too much excitation, or if it is under excitation, not that much excitation, or kind of so normal excitation, depending on that situation, depending on the magnitude or amount of excitation, power factor varies. For example, you see, I have written down the conclusion: over excitation, lagging power factor; under excitation, leading power factor; normal excitation, unity power factor. So soon I am explaining you that what does this means. You have to understand. But so the meaning of this on everybody look, that field excitation or simply the excitation of synchronous generator that is needed to build up the voltage, but simultaneously that governs, that influences the power factor. So in other words, power factor is dependent on the excitation, and depending on the excitation, it could be lagging, leading, unity. So when it will be lagging, meaning that is over excitation. So that is the question: why when the field current is too much, it represents the lagging. So I'm showing you through a diagram. Under excitation, why at that time it is lagging. So how it is related. And unity power factor, I said normal. Normal excitation means neither over nor under, kind of the so in between. It's a kind of the trade-off between over excitation and under excitation. It's a compromise between these two. That's why it is called the normal excitation. So therefore, everybody, you will be remembering this one. This is very, very important, that how the power factor is influenced by the excitation. So now let's have a look this one. First, everybody remember lagging power factor, then over excitation. So I'm going to explain you through the board, then you will get it. Uh, Let me clean up all those things. So therefore, first, let me discuss that. Sorry. Lagging power factor case. So for this case, we notice that it is the overexcitation, how it becomes overexcitation. And then now, at the beginning, everybody remember that voltage that is proportional to, as I said, the flux and speed, two factors. But we are assuming that this one is the constant because that is the speed. So this means we will be looking only that excitation, which is the phi. Now, everybody say we are considering the lagging power factor case. So therefore, for the lagging power factor, let me start with the voltage. For example, voltage is my reference. Let's say this is my reference, VI. So therefore, where the current will be located? So here it is the current, IA, right? That is the meaning of the lagging. So therefore, this is the lagging power factor angle. Now, you remember that diagram. So let me quickly. And so this is my terminal. And then I'm assuming that this is the flow of current. This was that internal voltage, EA. So air gap voltage was here. You see, E5. And then this was my RA, armature resistance. This one was that leakage reactance, XA. And this one was XAR. You know that few minutes ago we discussed this one. So this diagram will help you to draw the phasor diagram for the lagging power factor case. So everybody, you see that I started, this is the voltage. I'm drawing the phasor diagram of this one. This is VA and this is IA because lagging power factor. Now how I can represent this drop? I mean, from here, my goal, what I am doing, from here I want to go back there. I want to show the relationship between that VA, terminal voltage, and internal voltage. That is my intention. So everybody see, this is IA. So IARA, so I have to draw parallel to this one. You see? So this portion is my IA multiplied by RA. This is the voltage drop, you see, because this is my voltage. So from its tip, from its end, I added this one, IARA drop. And then what else? IA JXA. Of course, you know that this is J and then this is JXA. So now I have to add this drop, IA multiplied by JXA. So where it will go? You see, because this is inductor. For inductor, you know the relationship. IA, JA, IXA, that is the voltage drop in case of inductor. So you know, in case of the inductor, if this is voltage and this is current, then the voltage leads the current by 90 degree. This is voltage, this is your current, right, for inductor. So therefore, now this is my current IA. So therefore, IA multiplied by JXA, where it will go? It will be going like kind of here. I'm just showing by dotted. I will not draw it here. I'm just showing by dotted. You see, this will be your this one, JIAXA, the voltage drop. But because I don't want to show it here, so therefore I have to draw a parallel line to this one. So therefore, it will be here. So here that will be my JXA into I. Everybody, could you follow me what I'm saying? Are you understanding this one? So first, this was my, voltage, terminal voltage, this one, and then I drew this current, assuming that this is the lagging power factor case. So current is lagging, that is the theta angle. And now I have to, my goal is to go back there. I want to reach here in that way, in that direction I am going. So one by one, I am dropping the voltage drop. So IA voltage drop that I drew here. Why I drew like that? Because you see, IA was here, so parallel to this line. Just I am multiplying by RA. So IARA, this one. Then what is the next voltage drop? Next voltage drop is JXA and IA. So where it is located? This will be here. So you see, always I am starting from the end point of the previous voltage, VA. Then I added this one. From here, then I will go again from there. So these all are the voltage. Only this one is the current. So therefore, I was explaining that thing, that how to plot JXA. So therefore, this on this line your JXA into I. JXA into I. versus this on your eye. This means JXAI will be 90-degree leading. So this means actually from here you should go 90-degree in that way from this point. But because I want to go from the voltage endpoint, that's why I am drawing a parallel line to this one, which is this one, JIXI. So therefore now see, this means until that point, I have got this air gap voltage. Now everybody see, I am adding kind of this one. This is my E phi. This is my E phi, means air gap voltage. Then now consider this one, JXAR multiplied by IA. So again, because this is the same inductor, so they will be in the same line. So therefore I went further. So I added this portion, JIA multiplied by XAR. So now I am done. So everybody look. So now from here to here, this is my final vector, which is this one, EA. And then now I got an angle between EA and VA, you see, between EA and VA. That angle is called the delta. And that delta is called that power angle or the torque angle. That delta is called the power angle that we looked in the previous problem. This means delta is actually the angle between the EA and the VA. This means this is EA, this is VA terminal voltage. What is the angle? That's why in the previous problem, you found the angle with the EA, that angle was called the power angle. And then this is the theta. You keep in mind theta is the angle between VA and IA, between VA, which is the power factor angle. But delta is different. Delta is not the power factor angle. Delta is simply called power angle or the torque angle. Now, what is the conclusion here? What this diagram is telling me, everybody look, that EA, if you see this one, just by looking the projection, although I have drawn by hand, but at least you can guess that EA is much larger than VA. So that my conclusion is EA is greater than VA. EA is greater than VA. So, and then what is the meaning of the EA? EA is the internal voltage. And what are the factors upon which voltage depends? Flux and then the speed. But I said the speed is constant. So what is the main thing? Phi. And so what is the phi? Phi means that flux or the field current. This means that to get this amount of EA, you need high value of flux. That's why this is called the overexcitation. You have to put too much flux to compensate this lagging power factor case. This means that because the power factor was too much lagging, that's why you have to generate much higher voltage here. Otherwise, you cannot provide this voltage there. That is the meaning. Here the consumers are connected and they are consuming power, which are mainly the lagging power. Accordingly, that is causing lagging power factor. And to compensate that lagging power factor, you have to generate huge amount of the internal voltage here. This means, according to this equation, like voltage is proportional to flux speed, you have to provide huge overexcitation. That's why it is called that lagging power factor means overexcitation. Everybody, could you follow me what I am saying? Do you understand this vector diagram?
Yes, yes.
Yeah, okay. So therefore, once again, I mean, go back there. What I was explaining, you see, I am explaining this thing. I am learning effect. What is the effect of excitation on field current on power factor? How the power factor is governed, or in other words, power factor is lagging, then that is the overexcitation case. So overexcitation means you have to provide enough, very high value of the field current or the magnetic flux, phi value. That is the meaning when it is lagging power factor. Now I will show you another diagram. When it is leading power factor, you will see the opposite case. You need less excitation. I mean, pretty interesting. When it is lagging power factor, to compensate that voltage drop, you have to provide enough excitation. Otherwise, system cannot provide the required terminal voltage which is needed by the customers. That is the meaning. So that's why clearly you can understand that lagging power factor is not desired, because lagging power factor provides lots of voltage drop along the line in the system through the generator. Consequently, generator needs huge excitation, over excitation, to produce high amount of internal voltage, because there is drop, but customer wants a certain voltage. As a customer, your demand and my demand is that I want constant voltage, more or less, whatever the situation is. So that's why power operator needs to produce very high voltage with the expense of over excitation, because power factor is lagging. Customers are, and you all know that the power factor is basically the load current situation. Power factor comes not from the voltage, from the viewpoint of load, how customers are using the load, what type of load they are using. Is it inductive load or capacitive load or resistive load? Depending on that, power factor varies. So this means when customers are using much more lagging load, lagging power factor load, that time power operator or generator should provide high voltage, should generate high voltage with the expense of over excitation. This means this is the lossy system. That's why now, if customers use the leading power factor, their loads are mainly capacitive type, then you need to produce the less voltage. Generator needs only the small excitation, which is called under excitation. That is the meaning. So therefore now once again go back there, then you will get much more fun. Now I am deleting these things. I will keep this diagram, just I will delete this picture, and then I will keep everything as it is. Now I will delete this one. Now it is the leading power factor case. It is the leading power factor. Leading power factor case. So if it is leading power factor case, again do the same thing. You draw a vector diagram. Then you see what is the conclusion. So therefore let me start. This is my voltage. Now where the current will go, it is downward or the upward. If it is leading power factor, so definitely current will go upward, because the leading power factor, right? The current leading power factor means current will lead the voltage. Assume that this is the theta, power factor angle. Now again do the same thing. You start from here, I am starting from here, you reach there. So you apply the vector diagram. So what is my drop? IARA drop. So where it will be located? Here, the parallel to the IA. So this means kind of more or less like that. This is IARA. So this means so far I got VA plus IARA. Then you consider the same thing, IA, JXIA. So again, you see, this is because inductance. So therefore, what will happen in case of inductance? This is my current, voltage will lead. So this means my voltage vector will be here. I am not drawing the line, I am just showing you. Then that will be 90 degree leading, that drop, JIA into XI. But instead of drawing it here, I will be drawing parallel to this line. This means here, I will be drawing in that way. For example, this one, which is JIA and XI. So therefore I got this one. This means now you can say that from this point to this line, this is your that air gap voltage. I got this one. I got this one. Then now add this one, IA JXAR. This means again it will go in the same line. For example, JIA and then XAR. So then I am done. So now this is my final vector, this one. You see, this one is my now EA. So therefore, although you can argue that I have drawn by hand, I have made some partiality, but by just looking the diagram, what you can guess just by looking the projection, that in this case, EA is less than the VA. See, just look the projection. This was my VA. So, and then I add this one and this one and this one. Now EA. So just by looking the projection, you can guess EA is much less than the VA. So, and then what is that EA? EA is that internal voltage. And what are the factor? Again, the flux. I am assuming speed is constant. So the main thing is the flux. This means because EA is much less than the VA, meaning that I have to produce, generator needs to produce a small voltage with the expense of a small flux. So this means under excitation. And when I got that conclusion, I got that conclusion when my power factor is leading. So everybody, could you follow me? Is this fine? So this means when it is the under excitation, at that time it is the leading power factor. So, and then the last one, for example, see the unity power factor case. Power factor is neither lagging nor leading, it is unity. So therefore, I already said, so let me clean up this one. Now the unity power factor, then what? Unity power factor case. So in that case, what will happen? So now let me draw that vector diagram. So for example, this is my VA. So unity power factor, where the current will be located on the same line, right? So this is my IA. It is on the same line. There is no phase difference. Now then start. IARA, where it will be located? Because IA is in this on the same line, so it will be in the same direction. For example, this is my IARA, this amount. And then where is JIAXA? I mean, it should go here, 90-degree leading. So this means I have to go upward. So this means this portion is my JXA into I. So therefore, this means I got this one. This means this is this air gap voltage, if I, so far. And then you consider IAJXR, it is still in the same line. So for example, this amount, JXAR into I, and then this is my final vector, which is the EI. Now, although there is, that in real practice not equal, but kind of you can see EA is very close to the VA. So the E in this case, the conclusion is EA is pretty much close to the VA, terminal voltage. So meaning that you don't need much excitation, you don't need less excitation, kind of middle situation. And when I got this conclusion, when it was the unity power factor. So meaning that when the power factor is unity, customers are consuming mainly like resistive load. In that case, your terminal voltage and internal generator voltage kind of very close, almost close, a little bit bigger this one, but very close. Meaning that you don't need the very high excitation, even you don't need very less excitation, normal situation. Accordingly, conclusion goes for unity power factor case, you need normal excitation. And then again, all those, the concept goes power angle, the angle between E and B. And this is your delta in this case. So therefore, this diagram, this understanding will help you to solve the voltage regulation problem. For example, there is unity power factor related voltage regulation calculation. That time you have to keep this thing in mind. Like you have to find out this A and this is your terminal voltage, but this will be your diagram. And then I showed you the other two diagram for leading and lagging power factor case. So everybody, could you follow me? So
Yeah, it
therefore,
makes sense.
yeah, but because I drew this thing like by hand, so for you from the book, I have taken the picture so you can see. I mean, everybody, you will be just memorizing this conclusion. This is very important. I will be asking you this question in the another midterm exam or final exam, like what is the relationship between power factor and the excitation? So exactly you have to write this thing. Like always student like swipe these two and you say, and then they made the wrong answer. Don't swipe these two, don't interchange these two. Lagging power factor, then you need over excitation. Leading power factor, you need less excitation, under excitation. When it is unity power factor, normal excitation. And then, I mean, in a few class later, we will be studying synchronous motor. That time, like these two conclusion will be interchanged. For synchronous motor, when it is over excitation, it will be leading power factor and lagging power factor will come here. So then that is again pretty confusing, but still you have to remember all of those things. These are very, very vital and very important for synchronous generator. Uh, you see here actually those diagrams are available, because I drew by hand, but you can see here. The first one is for the lagging power factor case. You see, this is my voltage and this is the current and this is IARA, this is JIX, this is J. So this EA is here. You see the EA is much higher than VA. And this is for the leading power factor case. This is B phase, terminal voltage, the current is here leading, and then IARA drop, and then JIXA and JIXR. That thing I was showing you. So this is your EA. And then I think there is one more diagram. This one for the unity power factor case that I showed you last time. This is your terminal voltage. This is your current on the same line. This is IARA. This is JIXA. This is your air gap voltage. And again, you sum up this one, armature reactance drop. This is your final vector. So that's why if you look this, like EA is a little bit bigger than terminal voltage, but you need normal excitation. That is the meaning. So therefore, if you see the video, you can see my hand-drawn picture and explanation, but still I have made these things available. You all need to understand these things. So what I am going to do, like after today's class, I am going to assign you the third set of homework. The problem will be mostly on the synchronous generator. So far what we have learned. So using the voltage equation, and most problem will be about voltage regulation calculation. And that time you will be facing these things, leading, lagging, and unity power factor. Therefore, everybody please understand this thing clearly and then you attempt the homework. So once I upload the homework, then I am going to send you an email. And of course, you will get at least 1 week time. Now, moving forward, the parallel operation of synchronous generators. So parallel operation of synchronous generator means that in real practice, there are many generators which are running parallelly, which are running simultaneously or synchronously. That is the meaning, not just one generator. So therefore, you can easily guess why there is not only one generator. So therefore, here you see, I have written down those reasons, the 6 bullet points. So the question is, like I will be asking you this question, what are the reasons of connecting synchronous generators in parallel? I mean, why you need multiple generators? And then what are the reasons? Reliability, efficiency, maintenance, and then physical size, future growth, and flexibility. So therefore, let me explain you this thing, then you will get fun. Once again to the whiteboard. Let me clean up all these things. Okay, so what I am saying that, for example, sorry, this is one generator and this is powering to customer. It is powering to customer. Now, what we are learning now that why we need multiple generator. For example, this is another generator. And what I am saying that there should be a common, let me delete this line. There should be a common connection point. For example, let's connect these two generator and then power the load. You see this picture. So therefore, for example, this is generator number 1, Xeon, and this is generator number 2. What we are saying that let connect generator Xeon and G2 in parallel to provide the customers. That is the meaning. So that is the question, that is the reason why I have to connect G2 with Xeon in that fashion. You see, this means it has some voltage and it is providing some current ion. Similarly, it is producing voltage and it is producing some current I2, for example. And you see, in real practice, there are hundreds generator. Now I am explaining you with the just schematic of two generator, but keep in mind, in real practice, there are many generators connected in parallel in that fashion. So therefore, easily you can guess the current ion is coming from here, and then current I2 is going there. Definitely, this is the total current, right? So therefore, IT is that ion plus I2. So therefore, easily you can guess on thing that if you connect generator in parallel, then you can increase, you can provide more loads, you can send more power to the customers. Easily you can guess. Now, you saw that I mentioned 6 bullet points. What are the reasons of connecting these two generators in parallel? So everybody see, first point was the reliability. If you remember that slide, first point was the reliability. So therefore, what is the meaning of that? For example, this is your system. This is your system. Or initially assume that you have only one generator. For example, you have only this generator. And then that was providing to some customers initially. And now you know that time to time you need maintenance, you need some overhauling, or for example, there can be some short circuit, open circuit, there might be some issue. So therefore, for example, this generator got disconnected, for example, then the customers will be under dark. So therefore, under that situation, to handle those situation, if there would be another generator, for example, connected in the system, then at least this generator would provide power to the customers, right? It may not meet the total demand. It may not meet the whole demand, full load, but still it would meet some important loads. For example, think about hospitals or the fire station, police station, so bank, some important or the major loads, it could provide power. But when you have only one, then it is not able to meet that demand. So that's why when you have only one generator, that is not reliable. That's why the first bullet point was your reliability. That is for the reliability purpose. What you have to do, you have to connect many generators in parallel. So therefore, everybody understand that reliability. Second bullet was that efficiency. Second bullet was the efficiency. So this means that loads means basically these are the customers. Now, customers always does not need the full capacity. For example, at night, what do you do? At night, most of the loads are off. When you are sleeping, when you are on bed, most of the loads are off, except few bulbs, or your refrigerator is only running. But most of the loads are off. Similarly, even daytime, like when you are at school, for example, during normal situation, then most of the loads at your home are not using the power. So less power is being consumed by your loads. So this means there is variations of load demand by the customers. Customers always do not consume the full power or the full energy. Therefore, what power operator does, for example, for a certain moment, customers' demand is very low. If customers' demand is very low, that time what they do, they disconnect one generator. They say they no, for no reason the customers does not require the full power, but let's support the power only from the one generator. Let's provide power with the help of only one generator. Keep it safe. This means that when you are stopping it, meaning that you know that it has what is connected. It has the shaft system connected. You are saving the fuel input. You are saving the fuel input, right? Because it is not producing power. If it does not produce power, then you don't need to turn it. Your prime mover fuel input is stopped. This means you are saving the fuel input. In that sense, it is the efficient. It increases the efficiency. That is the meaning. But if you when you have only one and then if you take it out, then how the customers will get power? So definitely at least one generator should be running. But you see what is the load capacity, what consumers are demanding at particular time. If it is too less, then shut down the remaining generators and if possible run from only one generator, or in real practice 2 to 3 runs and then the remainings are off. And then definitely you can guess, especially during summertime, like typically noon or 1 p.m. is the peak time. That time most of the generators in the system run together, run parallelly, because that is the highest demand because of the heating, ventilation, and air conditioning system. So therefore, when you have many generators in parallel, you can maintain the efficiency. This means your system becomes efficient. That is the meaning. Now the third bullet was the maintenance. Third bullet was your maintenance. So therefore, maintenance means definitely that time to time, either this generator or this generator or any other generator connected in parallel need to go for maintenance. Therefore, don't maintain maintenance for all generator together. Go one at a time. For example, let's go the maintenance this generator. This means you disconnect it. Therefore, definitely this generator is providing at least some of the important parts. So therefore, that's why for maintenance purpose, you need generators to be connected in parallel. Now the fourth bullet was the physical size. The other point was the physical size. What is the meaning of that? Now, now you can make argument that, hey, I don't want to use many generators. There are 100 generators. Let's disconnect or shut down all 99 generators. I want to provide power only from one very big size of generator. For example, you argued that, okay, my generator size is not that one. I will make this huge size of generator. Because you know that if you can put more coil, then it will produce more voltage. So that is your argument. And then let's say your argument is that I want to provide a 1000 megawatt load with the help of only one generator. I will have like 1100 megawatt generator because I can increase the size. Now, theoretically, you can do that, but that is not practical. That will not be economical. For everything, for every component has some size limitation. You cannot make whatever you like. That will not be economical. That's why for economical purpose and for limitation of size purpose, you need multiple generators in parallel. That's why physical size is a constant. Like everything has some sort of limitation and capacity. So that's why to meet this type of huge amount of load, let's connect many generators in parallel. Don't increase the physical size. That's why to limit the physical side, you have to connect generators in parallel. So the next point was, I think, the future growth. The next point was the future growth. So what is the meaning of that? Now, for example, you have two generators that is meeting the demand of 1000, for example. Now, what happens as the days goes, consumers demand will increase. For example, now their demand is 1500 megawatt. After installing these two generators, 1500 megawatt. So therefore, how these two generators will provide 1500 megawatt? Because they don't have such capacity. Therefore, if you have other generators connected in parallel, only then they can support that one. So that's why from the viewpoint of future growth, you have to keep in mind that as the days go, consumers' demand will increase. So is it highly likely that there will be future expansion, future growth? Because as the days goes, much more digitalized, much more modernized, people need more and more power. Easily you can guess that. Therefore, from the viewpoint of physical growth, it makes sense to connect many generators in parallel to meet the growing demand of the future customers. And then the last bullet was, I think, the flexibility. Flexibility. What is the meaning of that? Now, there are some industry, for example, mine mills, lumber mills, some sugar mills, paper mills. There are various types of industry, and they use huge size of induction motor and synchronous motor. Now, they always are not dependent on the grid power from the system. They have their own generation. For example, this is on, sorry, for example, this is on industry and they have their own generation. And then they are powering their induction motor. For example, this is induction motor. Now, what is the flexibility means? They have their own generation. This is the industry and they are meeting their demand. That is fine. But again, this generator may need to go for maintenance, for example. So the day they will be going maintenance, they cannot run the motor. That's why if they have the provision to be connected to the main grid, then when they are going, uh, for example, they are going maintenance, this generator is disconnected, at least they will get power from the grid. So therefore, what they do, they make this type of connection. Typically, they connect a switch here. So they do a switch here, for example. It is their switch and it is the connection. Basically, it's a circuit breaker. This is that. They say that, the industry say that if we are able to provide power from our own source, then we will not be taking the power. On the other hand, the day it will go for maintenance, this one, then they will be connected to the system. This means industry want flexibility. They want flexibility. They don't want to be connected always to the grid. If they need power, only then they want to be connected. Otherwise, they can go with their own power. That's why to provide flexibility to the industry, they go with that parallel operation system. Therefore, these all 6 points are the reasons why generators need to be connected in parallel. You all will be remembering reliability, then efficiency, maintenance region, physical size, future growth, and then the flexibility. These are the 6 points that make sense to connect multiple generators in parallel. This means they will run together to meet the consumer's demand. Everybody, could you follow me?
Yes, that makes sense.
Yes, yes. Now the question is, now I want to ask you one question. Everybody see, what will be the voltage? What will be the voltage? I mean, you see, I am connecting in that way. So what is your guess? For example, this generator is producing V1, this generator is producing V2, this generator is producing V3, and then I am connecting in that way. So what is your guess? Is this voltage the same voltage or they have the different voltage? What is your guess? Should they have different voltage and then you will be connecting in this line? I mean, current can be different. Here it is I1, it can be I2 here, current can be different. But what about the voltage? Should the voltage be different? No, the answer is no. The voltage will not be different. So that's why there are, I mean, in a minute I will release you. I mean, I think you have the next class. You see, here I have written something. To connect to generator in parallel, the following condition must be met. You have to meet these 4 conditions. Their RMS voltage should be the same, phase sequence should be the same, phase voltage of all the generators should be same, the frequency should be the same. Only if these 4 conditions are met, only then you can connect 2 generators in parallel. Assuming that one was running and you want to connect a new one with the system. Therefore, the new generator, which we call the incoming generator, they must meet these 4 conditions. So I think I will explain you this at the beginning of next class. This is pretty interesting. And this will be one lab. Your lab number 6 will be exactly this slide. This slide is your lab number 6. So at the beginning of next class, I will explain you this thing. And so why we need these 4 conditions. And if any of the conditions do not meet, then what will happen? So I will be discussing these things at the beginning of next class. Okay, so is everybody fine?
Yeah.